This takes us to the next subsection. Is to get to that advanced idea of integration, we need to take a small detour towards how to interpolate a function. Okay. Again, this is something that many of you are familiar with. We will just formalize this. Again, we are talking about functions that we want to integrate, but it cannot be done analytically. Okay. That is our approximation. Here there is a very powerful theorem called the Weierstrass approximation theorem in blue font over here, and it basically says that if I have a continuous real valued function f that I want to integrate, so it should be well behaved, no funny jumps in the function, and you have given me some interval, then if you tell me your tolerance, let us say epsilon is some small number, then there always exists a polynomial function p such that it approximates f to less than the given tolerance. Okay, for all x within this interval. Okay, so this is named after Weierstrass. So you can see the power of this theorem, that is telling me give me any function, it can be some Hankel function, Bessel function, any complicated function. What this is telling you is that I can find you a polynomial function which approximates this guy very well. How well? It is up to me, right? If you specify epsilon, I will find you a p which approximates this function very well over here. Okay. So this is again not very surprising. You saw that with, for example, if I take 2 points over here, with 2 points I can perfectly put a, what can I do? What kind of a polynomial can I fit with 2 points? Linear, right? So this is a line. Okay. 3 points I can do a parabola. Okay. And so on. So 4 points, and so basically when I go to order n, supposing I say I want to interpolate a polynomial on n points, what will be the degree of the polynomial? N minus 1, right? Put n equal to 2. What is the order of the polynomial? 1. So always you are off by 1 degree, right? So I can fit a poly of order n minus 1. Okay. So there is a systematic way of doing this, which we will talk about, but I mean just think about it. Supposing I gave you 3 points and I asked you to fit a parabola, so what would you do? I have given you 3 points, x0, x1, x2. Okay, so I have given you these 3 points, x0, x1, x2, and I tell you fit me a parabola through this point and the functions, I mean through the function values at these points. So what would you do?
So you have 3 points, you fit a parabola.
Yeah, you have 3 points, so you have the functions.
You can connect them.
Huh.
Connect the 3 points and then, yeah, and then draw normals. That will be the focal point of the parabola.
Okay, but these points can be anywhere. I mean, they need not be uniformly spaced. They could be 1 point here, 1 point here, 1 point here. Assume the equation of a parabola. So I can say that, so say p of x is equal to, so say a naught plus a1x plus a2 x squared. Right now I know I have given you p of x naught. The value of the function has been given to you. So you get a naught plus a1 x naught plus a2 x naught squared. Like this I will get 3 equations in 3 variables, right. And the solution to this will give me a0, a1, a2. Right. So similarly, I can in general reproduce this process for a set of n points also, right. So I will be solving a system of n equations to get these n points. Now it turns out you can do it like that, there is no problem. It turns out there is a more clever way of constructing this polynomial, and that goes after the name of a famous scientist called Lagrange. So these Lagrange polynomials, I will write them down over here. So you have Li of x. So I will just write down the form and then we will investigate it. Okay. So this big pi stands for product. Okay. So, before we get into more details, just look at this. I have constructed some function over here. So, its product, how many terms are in the product? N minus 1 terms are there in the product, because j not equal to I, right. So, j is equal to 1 to n, but j not equal to I. So, it's a product of n minus 1 terms. So, this Lix is a polynomial of what degree? N minus 1. There are n minus 1 terms, each term has a x minus something. So, the overall degree is going to be n minus 1. Okay. Now, this function looks quite interesting, right. So, supposing I ask you what is the value of the function Li of xi? What is its value? Each term cancels off and its value is 1. Okay. Li of xj, okay, where I not equal to j. What is this value? 0, right. So, if I write, if with using this function over here, using this so called Lagrange polynomial over here, can I write f like this? So, I can write this as so, first of all, is this expression that I have written over here on the right hand side, is it a polynomial function? Let us look at it one by one. What is this guy? Is this a constant or is it a variable as a function of x? It's what is its argument? Xi. Xi is a fixed point, right. There are n points and this is taking the ith point. So, this term over here is a constant. The next term over here, Li of x, what is it? It is a polynomial order n minus 1. So, this is a poly order n minus 1. Okay. What is the sum of any number of polynomials of order n minus 1? N minus 1 at best, right. It can be lesser also, but at best it will be n minus 1. Okay. So, what I have done is I have given you a function which is of order n minus 1. So, it has order n minus 1, and does it agree with the value of the function at the given nodes. So, I have given you n nodes. Okay. So, n nodes are this x1, x2, xn. So, f of fn minus 1 of xi, what is it equal to? We will use this property over here. So, there are n terms in the summation. Of this n terms in the summation, which term will survive? Only one term will survive, because these Lagrange polynomials, they are such that they are 1 only for this I equal to this I, but if this I and j are different, then it becomes 0, right. So, in this summation over here, there is only one term that will survive when I substitute xi, right, and that term will have value will be 1 from here, and what will be left here is simply f of xi. Okay. So, keep in mind, my original function f was not a polynomial function. Okay. It was any continuous real valued function, and out of that I have created this guy over here, which is a polynomial function. In circle is a polynomial function, and this polynomial function, it agrees with the value of this arbitrary function at n points, right, and it is a polynomial of order n minus 1. So, what you did in a slightly clumsy way by solving a system of equations over here, you can do in a little bit more systematic way over here. Okay. So, this is, I mean, the reason why we use this is, again, it makes the mathematics as we go further on very simple. It is also very elegant. Just look at the way this function is created, right. It's such a beautiful thing that it goes to 0 at all other points except at the point that you're looking at it. Okay. So, having done that, now let's go a little bit further. So we wanted to integrate a function, right? So, there is a function that we cannot integrate analytically. So, step 1 is we created some approximation of it, a polynomial approximation of it. If you give me n points, I give you a polynomial of order n minus 1, because that is the best I can do. If you give me 3 points, I can give you a parabola. I cannot give you a cubic, right, because there is not enough information there. Okay. Next, we will try to integrate it, right. So, why do you think we first took, instead of directly approximating the function, directly integrating the function, why did we make this change to polynomial? Our objective was to do this.
Because polynomials are easy to do.
Exactly, right. I do not know how to integrate this because it is non-integrable, but I am approximating it by a polynomial, and polynomials I know we can integrate by hand, right. So, the step 1 was to find a good approximation. Okay. So, now let us just do the obvious, let us integrate this expression that I have. So, this was my original function. Know that this is a approximation. Okay. It's a approximation of order n minus 1, that is the function that we had from before, and we will just put this in over here. So, f, this term over here, I am going to replace it by what I had already used before. So, that is going to be a summation of f of x I Li of x dx, okay, I is equal to 1 to n. Okay. So, I have just rewritten what I had done previously. Remember, this is a integration sign, the variable of integration is x. So, what do you think I should do next? Can I simplify this expression? Can the integral sign move anywhere? Okay, this guy, what is this guy? This guy is a constant. So, I can move this integral sign further inside over here, right. So, I can write this as I is equal to 1 to n, okay. Then I am going to have f of x I integral x 1 to x n Li x dx, right. Okay. This thing over here, this term that I have written over here, does it depend on the choice of function f? Not at all, right? There is no f over here, right? So, that is see the power of that. So, now I can rewrite this expression as I is equal to 1 to n f of x I w I, where this w I is some other w I, right, this expression over here. So, would you call what we have done also a quadrature rule? It is a quadrature rule because it is giving me an approximation of the integral. It is telling me what all I need to know, function value at a few discrete points. So, these are the xi nodes and weights that do not depend on the function, right. That is the important part of a quadrature rule, that the weights are independent of function chosen. Okay. So, another advantage is that this wi, what you can do is you can pre-compute and keep it. You can store it as a table. You do not have to solve it when you are actually, when you are given an integral. It is not that time you should start to compute wi. You can pre-compute and keep it. In fact, there are many libraries, mathematical libraries, which will tell you the values of w for various, various intervals or whatever. Right. So, these can be pre-computed. So, when you get your function that you want to integrate, what do you have to do? All you need to know are the nodes, calculate the function values at those nodes, multiply by pre-computed weights, right. So, this we should do pre-computed. fine. Okay. So, this has given us a systematic way where we have calculated the approximated the integral of a function to order n minus 1, and for that how many points we need? N points. Okay. So, this is as far as interpolation goes. Now, there is, you will be surprised to know that if I told you the result beforehand, now we want to make this even better, you know. So, even better means what? Supposing I tell you that the number of points at which I want to evaluate my function is fixed, n points, you have no choice over it. Can you somehow give me an answer that is accurate to a higher order of polynomial? No, right? Order n minus 1 is the best I can do. Okay.